Alright, this is the lecture video for Chapter 5, Newton's Laws of Motion. So, main topics for Chapter 5 include different forces and masses, how they're measured, Newton's first law of motion, his second law, his third law, the vector nature of forces, because you will have forces in 2 dimensions. So therefore, force is a vector. Weight and normal forces. So the most basic definition of a force is it's either a push or a pull on an object. Plain and simple. Force is a vector. Therefore, it has a magnitude and a direction associated with it. So just like before with vectors, we'll typically set up our coordinate plane to match a graph just to make our lives easier. All right, so mass. One definition of mass is how hard it is to change an object's velocity. If you have an object that has a bigger mass, it's going to be harder to change the velocity. It can also be thought of, and this is probably the definition you know more, is that it's the measure of the amount of matter in an object. So however much stuff makes up your object is its mass. Mass of an object does not change between places, whether it's on Earth, in space, Mars, wherever. The only way the mass changes is if you physically alter the object itself. All right, so Newton's first law of motion is also known as the law of inertia, and it says that an object that stays in motion will continue to be in motion, or if an object is at rest, it is going to stay at rest. So in the real world, if you roll a ball across the floor, right, eventually it's going to stop because of friction. In the ideal perfect physics world, that ball would just keep rolling and rolling and rolling until something stops it. So that's Newton's first law of motion. An object is going to stay what it's doing unless some other force acts on that object. So in order to change the velocity of an object, you need some sort of net force. And a net force is just the total amount of force acting on an object in a certain direction. For Newton's second law of motion, this is more of the quantitative side, so the equation part of Newton's laws. So for example, if you have a spring scale, which is what these guys are used to measure force. If you have 2 equal weights, so here are your weights down here, if 2 equal weights exert twice the force of one, you can use this to calibrate a spring, which you may do more in your lab settings. So if you have one weight, you have F1, whatever value that may be. If you put another one on, same mass, then you have twice as much force as the first one. Once you have a calibrated spring, you can do more experiments and look at the acceleration, the force, and the mass of your objects. So with that being said, our equation for Newton's second law is the famous F equals ma. So with this, we can say that acceleration is proportional to the force. That means if acceleration goes up, then the force is also going to go up. And likewise, if acceleration decreases, then the overall force is also going to decrease. They are proportional. They are going to do things in sync as long as your mass stays constant. On another note, mass and acceleration are inversely proportional. This means that they're going to do the opposite of each other. So if you increase the mass, then your acceleration is going to decrease. Like in the example shown here, if you double your mass, then your acceleration is going to be cut in half. Because doubling is essentially saying 2 times as much. The inverse of 2 would be 1 over 2 or 1/2. So based off of that, we get our formula. And most commonly you will see it written this way, but you can of course rearrange to solve for whatever variable that you're looking for. So in the case that your object has several forces acting on it, so maybe it has 2 forces pushing on it or 2 forces pulling on it, then you say that the net force, or the sum of your forces, is equal to the mass of the object times its acceleration. So sigma just means sum of. You add your forces that are in the same direction, you subtract them if they're going opposite directions, just like you did with vectors. So your units for this formula, we are only going to focus on the SI units. So mass is measured in kilograms, acceleration is in meters per second squared, and your forces are measured in newtons. Here are some examples of forces that are in newtons already. So the weight of an adult human is roughly 700 newtons. You can see as your objects get bigger, you have more force on it. And then smaller objects have smaller weights, smaller forces. So to help us use the equation for Newton's second law and to find those sum of forces, we do what are called free body diagrams. And all a free body diagram is it has the object and it shows you all the forces acting on said object and in their respective directions. So you first need to draw your object of reference. So I draw boxes for all my objects. That's all you really need to do. And then you sketch your forces. So this will be shown later too, but you usually have at least 2 forces acting on your object. You have what's called the force of gravity, or sometimes it's referred to as the weight of the object. So weight is measured in newtons, and we'll see that later on. But then the mass is still in kilograms. Mass and weight are completely different from each other. Mass is how much matter makes up an object, while the weight of an object relies on gravity. Your other most common force is your normal force. Sometimes it's written as Fn, or sometimes it's just written as capital N. Either one works. This force, and we'll talk about it in detail in a few slides, is always perpendicular to your surface. So if your object is sitting flat on a horizontal floor, your normal force points up. If your object is on an incline, then your normal force will be at an angle. So here's another example of free body diagram. So we have our coordinate system that we've been using. Part A is the physical picture of what's happening. B is your free body diagram. So you have the weight pulling down on the object, and then you have the upward force that the hand is exerting going up. This can also be your normal force as well. Sometimes it goes by different names. So, Newton's third law of motion is more commonly referred to as the action-reaction law. That means for every force that is acting on an object, that object is exerting the same force back. So if you are pushing on the wall, you are exerting a force onto the wall, but the wall is also exerting a force back on you. You push against the wall is pushing back at you, just in the opposite direction. So that's why you have the different signs here. Remember, negatives just show you direction, that's all. So here's some action-reaction pairs. You have the car on the ground exerting a force, and then the ground is exerting a force back onto the car in the opposite direction. You have a person pushing on an object is pushing back on the person, so on and so forth. So with the action-reaction law, the forces acting on each other are equal, despite how big or how small your objects are. What does change, however, is the acceleration of your objects. If your objects have a smaller mass, you're going to have a bigger acceleration. Bigger masses have smaller accelerations. So when you have contact forces, which means the forces on the objects are physically touching each other, you have the force acting on the first object, and then the force acting from the first object to the second object. So with that, we talk about forces in 2 dimensions, and it works the same as projectiles. Exactly the same trig functions, same frame of reference, same equations. So going more into detail about weight. So the weight of an object is also referred to as the force of gravity, or gravitational force. To find your weight, you take your mass of the object in kilograms and multiply it by little g, so 9.8 meters per second squared. Multiplying both of those gives you the weight of your object in newtons. So weight is measured in newtons. It is a force. It relies on gravity. Weight changes depending on where you're at. So if you go to the moon has a smaller acceleration of gravity. Therefore, your weight is going to seem smaller. You can also have what's called an apparent weight, or a relative weight, depending on where you're at and the acceleration. So the most common example for this is in an elevator. So if you go in an elevator and the elevator goes up, you feel like you're getting heavier. If you go down an elevator, sometimes you feel like your weight is smaller. So it depends on the direction of acceleration and your weight. Normal force. So normal forces is the force exerted by the surface to your object. So if you have the can on the counter, then you have the force of gravity pulling down the can, but then the counter has an equal and opposite force, in this case because you're not moving, up onto the can. This force is also perpendicular to your surface. It can be equal to your force of gravity if your object has a constant velocity or at rest. It might be greater than or less to the force of gravity or the weight. It just depends on the situation. So the normal force is always perpendicular to your surface. So if you have your object and it's sitting on a flat surface, normal force is going to go up. It forms that right angle with your surface, so therefore it is perpendicular. If you're on an incline, like the guy here, so here's your guy, force of gravity pulls down, right, and then the box also has force of gravity pulling down as well. Forgot to mention that part. But for the incline, force of gravity points straight down, no matter what angle you're at. The normal force is going to be perpendicular. So since the surface is in an angle, your normal force is also going to be at an angle, but it's still perpendicular, forming that right angle with your surface.